handle it, all right? What's happening as x goes to infinity? So e to a number that's getting really, really big, just think about the graph of e to the x. E to the x look like this, right? What happens as I let x get big? That means if I go out this way on this function, what's happening? It's becoming infinite. So what's happening to this right now is this top left corner is headed towards infinity, isn't it? Now I'm going to subtract from that e to the negative x. So let me take a look real quick at e to the negative x. Here it is. What's happening as I go out to infinity on this graph? It's going to get really small and go towards what? 0. So that's going to 0. Then on the bottom, don't we have the same behavior except a plus between them? So we're getting something that's looking a lot like infinity over infinity, aren't we? Bless you. And so infinity over infinity is 1. No, it's not, right? Infinity over infinity is an indeterminate form. We don't know what that is, right? So what do? L'Hopital's rule, right? L'Hopital's rule will allow us to deal with this maybe not, okay? There's no guarantee that this is going to be pretty. Like I said, I didn't work this out before class, so let's see what happens. All right, let's apply L'Hopital's rule to that right here. So I'm going to say equals, and I'm going to let everyone know that I'm about to use L'Hopital's rule, so you're supposed to somehow indicate that. And the two different ways that normally you're taught is either to put an H here. How many of you saw that way? Okay. Or like an H with a circle, or an L with a circle, or something like that, right? I do L for L'Hopital. So I'm letting everyone know that this is equal to the following limit, x going to infinity. Now, L'Hopital's rule says all you have to do, if you have infinity over infinity, is take the derivative of the top and divide it by the derivative of the bottom, right? It's not quotient rule. So what's the derivative of the top? So what's the derivative of this? Itself, right? E to the x. Okay, minus, now what's derivative of e to the negative x? It should be itself, right? E to the negative x, but you have some chain rule here. You have to take derivative of what's up here also. And the derivative of negative x is negative 1. So you're going to have e to the negative x, but you're also going to have next to it negative 1. And that will wind up changing that minus to a plus, won't it? And then on the bottom, we're going to get the same thing, e to the x plus e to the negative x times negative 1. And what do we get here? E to the x plus e to the negative x over e to the x minus e to the negative x. And have we actually gained any ground here? No, because we're still going to get infinity over infinity again. And we're going to just keep on cycling through, right? The next time we do this, if we try L'Hopital again, it's just going to change that to a minus, that to a plus. We'll be back to where we started. And hopefully in your Cal 1 class, if you did L'Hopital, you were taught that, hey, it's a great tool, but sometimes it doesn't work. And this is one of those times where it doesn't work. So anything else? If you do quotient rule, then you're taking a derivative of this, and that's just going to give us a derivative of a function that's going to give us a new function that has nothing really to do with the original. So we want to know about this one. So anyone have any other suggestions? Now this is a straight limit. I mean, we just have to see where it's headed. Any? Logarithmic? That would be something we could do. Usually we bring in the logarithm if we have something like 1 to the infinity or like infinity to the 0. Then we bring in the logarithm so we can pop the powers out front and use L'Hopital. So I don't see this as being obvious. I mean, I know what I want to do next, but I'm curious if anyone else has an instinct as to what to do. Okay. So let me go to this original one. Let me try something completely different because I think Hopital is not working here. So let's do this. Let's just take a look at this expression. I'm sorry? How do you mean? Sub what? You want to... I think we're still going to have the same issues because eventually you have to replace that a with infinity and we'll still get the same behavior. How about this? I'm going to try something. No guarantees here, okay? This may not work. All right, so let me just take this right here, what's in the box, and let me just write that down. And I'm going to write it like old school style. Right? This is old school. It's long division. And let me try this. So the way I did long division before is I said, okay, what do I multiply this by, right, to get this? 1. Okay, so I'm put a 1 here. And then I take that 1 and I multiply it here, put that underneath. Take that and multiply it here, put that underneath, right? Put that right here. So I'm going to have what? Plus e to the negative x. Y'all agree? And I come through and I subtract, which means I'm going to change the signs. So when I subtract, this becomes minus, right? And add down, and these two go away. And what am I left with? Negative 2 e to the negative x. Okay, and then maybe I try again. So it's going to be difficult for me to turn this into this. Do you all agree? To turn e to the x into e to the negative x is not going to be so easy. So let me just act like this is going to be my remainder, right? This is my remainder, so I'm going to put plus my remainder, negative 2 e to the negative x over e to the x plus e to the negative x. Y'all still with me? It's going to work. It's going to work. What am I going to need? Okay, all I've done is I've rewritten this expression as this expression, right? That's what I've done. This expression is equivalent to this expression, just long division, yes? It's a weird long division, but it's long division. And so when I'm taking a limit now, so that's this limit right here is equal to the limit as x goes to infinity of 1 plus negative 2 e to the negative x over e to the x plus e to the negative x, right? That's the same thing. I should put this in parentheses to be correct here. Did I press record? Okay. What is it that we think the answer is going to be? 1, which I'm pretty close if I can just make that go to 0. But it goes to 0. Let's take a look at why. If x goes to infinity, what does that go to? 0. We just talked about that a second ago, right? E to the negative x goes to 0. So the negative 2 doesn't matter. So if I look just at this fraction right here, this is headed towards 0. Over, now I don't want the bottom to head to 0, because if I get 0 over 0, that's just like infinity over infinity, and I don't know anything. But it's not. This goes to where? Infinity, and then plus this goes to 0, right? So I've got something that looks like 0 over infinity. And where does that go? Is that an indeterminate form? No, that is actually a good thing, because what's happening is your numerator is getting really small, right? Which tries to make the fraction small. The denominator is getting big, which helps the fraction get small, right? If your denominator gets bigger, your fraction gets smaller. If your numerator gets smaller, your fraction gets smaller. So you see these are just helping each other. So this is just headed to 0. So this limit is headed to 1. And that verifies what we saw in the picture. But that's how you would do it mechanically. Got it? Okay. So what's the lesson here? Hopital's great, but doesn't always work. And look at, in this class, you know, the way I look at, math, you've got this toolbox, right? All these tools that you've dumped in this box, and there's tools down there you forgot you had. you know? And this is an example of a problem where, look, I had to use long division. That's something I don't use all the time, but there's nothing off limits when it comes to a class like this. Every tool in that box is fair game, all right? So you always want to just keep hacking away at these things, try. Now, if this wouldn't have worked, okay, let's just say this wouldn't have worked, I would have waved my hands at this. Okay, I would have said, you know what, I don't see it right now, and we'll move on. And then I would have taken some more time on my own to go try and figure it out. But fortunately, it worked, all right? Okay, sorry about that. That's only off the right side, right? You went to 1 off the right. To go the other direction, you have to let x go to negative infinity. We would wind up using long division again. Okay, that's hyperbolic tangent. Hyperbolic secant looks like this. This one's a little more interesting than the ones we had before. We actually have what appears to be a vertical asymptote, right? And a horizontal asymptote. And if we have a vertical asymptote like this, that means that this function is not defined somewhere. Looks like at 0. Now, why wouldn't this be defined at 0? Because sine hyperbolic, right? If you go back and look at that graph, at 0, it was 0. And since cosecant hyperbolic is the reciprocal function, it would be undefined there and you would have your vertical asymptote. Make sense? Also, if sine hyperbolic's getting huge, then as you go out this way, 1 over sine hyperbolic, which is cosecant hyperbolic, should get small. Okay, I'm going to put cosine hyperbolic up here. And let's see if you can predict what secant hyperbolic would look like. Am I going to have asymptotes? Am I going to have vertical asymptotes? What do y'all think? No? I'm seeing a lot of heads shaking no. Is this ever going to be 0? No. So 1 divided by this will never be 0. Will never be undefined, right? So our secant hyperbolic should be well defined. Now, as we go out to the right here, it gets huge. That means as we go out to the right on its reciprocal function, it should get small. Same thing as we go out to the left, it should get small. And then what about right here at 0? It looks like it's 1 there, right? So if I do the reciprocal of that, 1 over 1 should be 1. So I have this point should live on my inverse, or not inverse, my reciprocal function. And as I go out to the right, it should like maybe dive down like this. That's what it does. Okay, and then tangent, cotangent, hyperbolic, there it is. Okay, we won't get into the details. I'm not going to quiz you on these. I'm not going to ask you to graph these. I just want you to, we're introducing you to a new function, right? So I want you to know what they look like. Realize that they don't look anything like the trig functions from pre-cal, but they are all still functions. We can graph them. All right, now, when you were in pre-cal, one of the important things that you learned in pre-cal was this thing called the Pythagorean Identity. On a scale of 1 to 10, 1 being like the most important thing ever, and 0 being like the sky is blue. Does that make sense? That doesn't make any sense. On a scale of 1 to 10, did I say 0? Okay, sorry. A scale of 1 to 10, with 10 being like the most profound thing ever, and 1 being like the sky is blue, which isn't very profound, is it? How important was this in pre-cal? What would you rate that as? About a 6, 7. Sky is blue? Okay, you should know it like the sky is blue. All right, you should remember that like the sky is blue. But as far as its impact, this was a huge formula, right? One of the main ones we want to take away from that class. And since we have these new classifications of trig functions, there are some identities that are important with these. And one identity that's really important is this one. It looks a lot like this one, doesn't it? except you have subtraction instead of addition. And anytime you have subtraction, order matters, doesn't it? Like you can't just flip it around, no big deal. You have to pay attention to that. So cosine hyperbolic squared x minus sine hyperbolic squared x should be equal to 1. And I want us to show that. Show it's true. So in pre-cal, do you remember there was a section, I'm sure you loved it, it was where you'd have to prove identities, right? Well, to prove an identity, how do you do that? How do you prove an identity? Anyone remember? What's that? Yeah, but I'm just saying, if someone says, hey, you need to prove this is true, how do you go about that? What's the standard sort of approach? You manipulate it. You're on the right track, but not plot. Okay, what's that? Who said that? You have to start on one side and turn it into the other side. You are not allowed to treat this as if it's true right now. All right? So right now you can't be like, oh, I'm just going to move this to the other side of the equation. You can't do that because we're trying to prove that that's an equation that's true. So what I need to do is start with one side and massage it into the other side. Now the side that you start with is usually the more complicated side. Because if I write down 1 and have to turn it into this, 1 isn't a lot of things, isn't it? Right? 1 would be hard to just transform into the other side. So I'm going to start with the more complex side. So I'm going to write LHS, which stands for left-hand side. I'm going to write down the left-hand side. And my goal here is to work with that and eventually get 1. All right. The only thing I know about cosine hyperbolic x and sine hyperbolic x is their definitions that were presented in the beginning of class with the e's, right? So I'm going to just start writing them down. Cosine hyperbolic x, that was what, 1/2 e to the x plus e to the negative x, right? That's cosine hyperbolic x, but I got a square, right? So I'm going to just put this in brackets. I could use parentheses, but I'm going to use brackets. That's what that means, right? Then I need to subtract from that this one squared, so I'll do another bracket here. And in here, 1/2 e to the x minus e to the negative x. I can do something with the 1/2s, but not until I take care of the squaring that's happening to them, right? Because this square is applying to the whole thing. So that means you have to square the 1/2 first. So that's exactly what I was going to point out next, is that, look, if you have like a times b squared, this is a squared times b squared, right? The squared goes to both if there's multiplication here. So I have multiplication right here and right here. So I've got to square the half and then square this, right? So I'm going to square the 1/2. That's going to give me 1/4. Then I'm going to have to square this, e to the x plus e to the negative x. I'm not quite ready to square that yet. Minus, over here, I've got the 1/4 again, squaring the half. And then, I forgot a parenthesis there, right there. I've got to take this e to the x minus e to the negative x, and I've got to square that. All right. We're on our way. How about some squaring now? What I'll do is, this is going to be scratch work over here. SW for scratch work. This is just me working some stuff out, and I'll come back over here. So if I were to take e to the x plus e to the negative x and square it, right? That's this. That means I multiply it by itself, times itself. Okay? So all I'm doing right now is this piece right here. Just doing it on the side to figure out what it turns into. And to do that, I can just expand it. Right? That's what the technical word for this is, expanding this. Or if you like FOIL, we can use FOIL because it's 2 terms, right? 2 and 2, so you can do FOIL. But we should just all know the pattern, right? It's this times this. So what's e to the x times e to the x? Most students are going to tell me this, e to the x squared, and then other students are going to tell me e to the 2x. And which one is it? That's a trick question. It's both. They're both correct, okay? They're both correct. E to the x times itself is e to the x squared, right? But if you have something to a power, you multiply these powers, and 2 times x is 2x. All right? So are we OK with the fact that this times this is either one of these? I'm going to use this one. OK? So this is e to the 2x. All right. This times this. Close? No?